What if every human on Earth vanished right now? Imagine the silence, no voices, no footsteps, just the hum of machines left behind. But how long would our lights, those glowing symbols of human ingenuity, keep shining in a world without us? Pause for effect. The answer, ISNT, what you think, and it reveals a future where technology might outlast us all. Welcome to Future Unveiled, where we dive into the unknown to uncover truths that will blow your mind. Stick around to discover when the last light goes out and what it means for our legacy. Imagine this. It's a regular Tuesday morning, and the world is alive with the chaos of humanity's 7.8 billion of us, give or take, powering cities, factories, homes, lives. Skyscrapers blaze with light, streetlights guide early commuters, and your coffee maker hums in the kitchen. Then, in a single, inexplicable moment, every human on Earth vanishes. No warning, no catastrophe, just gone. The streets are empty. The air is still. The only sound is the faint hum of machines left behind, running on borrowed time. Welcome to the vanishing afterthought experiment that forces us to ask, what happens to the world we built when we're no longer here to hold it together? Let's set the stage. Our cities, our homes, our entire civilization runs on electricity. Those glowing lights are the pulse of human ingenuity. From Times Square's dazzling billboards to the lone bulb in a rural cabin, they're all tied to power grids, intricate networks of plants, substations, and wires that span continents. But here's the harsh truth. Those grids are fragile. They're not built to run themselves. Without humans to flip switches, refuel generators, or fix broken lines, they're like a house of cards waiting for the first gust of wind. A 2024 analysis on infrastructure resilience estimated that fossil fuel plants, coal, gas, oil, which supply about 60% of global electricity, would grind to a halt within hours to days. Why? Because they rely on constant fuel deliveries, trucks hauling coal, pipelines pumping gas, all orchestrated by human hands. Think about it. A coal plant might have a few days' worth of fuel stockpiled, but without workers to manage boilers or clear ash, automated systems would trip, shutting down to prevent catastrophic failures. Natural gas plants, which power much of North America and Europe, might last a little longer, maybe a day or two, before pressure imbalances or unmaintained compressors cause a cascade of shutdowns. Even the most advanced grids, like those in California or Germany, depend on human oversight to balance supply and demand. A 2017 discussion on infrastructure decay noted that urban grids could fail in as little as 72 hours without intervention, plunging cities into darkness. Picture New York City's skyline, once a beacon of human ambition, going black block by block. Tokyo's neon districts, silent, your neighborhood streetlight, flickering, then gone. But it's not just about electricity. The Vanishing Act reveals how interconnected our systems are. Without humans, water pumps, stop cooling systems fail. And even backup generators, those humming in hospitals or data centers, run dry when their diesel tanks empty. A single unattended fault, like a transformer overheating or a circuit breaker tripping, could trigger a domino effect. Imagine a world where the lights that defined our night stadium floodlights, airport runways, even the glow of your phone screen start to fade. It's not just a loss of light, it's the unraveling of the infrastructure we took for granted. And yet, some lights, in the most unexpected places, might hold on longer than you'd think. This is just the beginning. The question isn't just when the lights go out, but which ones last the longest stand, what they reveal about the legacy we leave behind. Let's dive deeper into the systems that might keep humanity's spark alive, even when we're gone. Let us dive into the heart of humanity. Power the electrical grid and ask, how long can it keep the lights on without us? Picture the grid as a vast, interconnected web stretching across continents, humming with the energy that fuels our cities, homes, and lives. It's a marvel of engineering, but it's also a fragile beast, dependent on constant human care. When every human vanishes, the grid's last gasp begins, and the countdown to darkness starts ticking. This isn't just about lights flickering out, it's about the unraveling of a system that defines modern civilization. So, let's break it down and explore how long the grid can hold on, why it fails, and what it tells us about the world we leave behind. First, let's talk about what powers most of the world. Fossil fuel plants. Coal, natural gas, and oil generate about 60% of global electricity. According to a 2024 report on energy infrastructure, these plants are the backbone of grids in places like the United States, China, and India. But here's the problem. They're not self-sustaining. Coal plants, for instance, rely on a steady stream of fuel delivered by trucks or trains. Without humans to drive those trucks or maintain those supply lines, the fuel runs dry fast. Most coal plants have, at best, a few days' worth of coal on site. 2017 Quora thread on grid resilience estimated that these plants would shut down within hours to a couple of days as automated systems detect fuel shortages or operational imbalances and trip to prevent damage. Picture a massive coal plant, its furnaces cooling, its turbines grinding to a halt as the lights it powers blink out across entire cities. Natural gas plants, which supply a huge chunk of electricity in places like Europe and North America, might last a bit longer, maybe a day or two. Why? Because gas pipelines can maintain pressure for a short time without human intervention. But pipelines aren't magic. They rely on compressors, valves, and monitoring systems that need constant maintenance. A 2021 study on energy system vulnerabilities noted that unmaintained gas plants would face cascading failures as pressure drops, leaks develop, or automated controls detect anomalies and shut down. Even in the best-case scenario, where a plant has a large gas reserve, it's unlikely to run for more than a week. The grid, designed to balance supply and demand in real time, can't handle the chaos of unattended systems. One fault-clogged valve, an overheated transformer can trigger a domino effect, taking out entire regions. Now, let's consider the urban grids themselves. Cities like New York, Tokyo, or London are powered by complex networks of substations, transformers, and distribution lines. These systems are built to handle constant fluctuations in demand, but they're not designed for neglect. Without humans to monitor and repair them, small issues snowball. A 2019 analysis of grid reliability highlighted that urban power systems can fail in as little as 72 hours without maintenance. As circuit breakers trip, transformers overheat, or power surges cause outages. Imagine Times Square's dazzling billboards going dark, one by one, as the grid beneath it collapses. In smaller towns, the story's similar local substations might hold on for a few days longer, but without fuel or repairs, they're doomed. Even backup generators, like those in hospitals or data centers, rely on diesel tanks that run dry within days or weeks, assuming they don't overheat or break down first. But it's not just about fuel. The grid's fragility comes from its interconnectedness. Power plants, substations, and distribution lines are like a symphony orchestra. Every part needs to play in harmony. When humans vanish, that harmony falls apart. Cooling systems, essential for keeping plants and transformers from overheating, rely on water pumps powered by the grid itself. If the grid falters, those pumps stop, causing plants to shut down to avoid catastrophic failures. A single broken line, say, a tree falling on a power cable in a storm, can isolate entire regions. A 2023 ex-post by an energy engineer speculated that rural grids might outlast urban ones by a few days, thanks to lower demand and simpler systems, but even they would succumb within a week or two as equipment degrades or weather takes its toll. What about the so-called smart grids we've been building? These advanced systems, used in places like Germany and California, use automation and AI to optimize energy flow. Surely, they'd last longer, right? Not really. While smart grids can self-correct minor issues, they still need human oversight for major repairs or fuel management. A 2024 IEEE report on smart grid resilience noted that even the most advanced systems can operate autonomously for more than a few days without human intervention to address hardware failures or external disruptions, like storms or flooding. And let us not forget nature's role without maintenance crews to clear debris or fix storm damage. Grids face a losing battle against entropy. A single hurricane or heatwave could accelerate the collapse, turning cities dark in hours instead of days. Now, let's zoom out and think globally. Different regions have different grids, and their fates vary. In countries heavily reliant on fossil fuels, like India or Australia, the lights would go out fastest within days. In places with diverse energy mixes, like Norway with its hydropower or France with its nuclear plants, some pockets might hold on longer. but we'll get to those in later chapters. For now, picture the global grid as a patchwork quilt, unraveling at different speeds but all heading toward the same fate: darkness. A 2020 study on global energy systems estimated that without humans, 90% of the world's grids would fail within a week, with only remote or highly automated systems lasting longer. This brings us to the human element, or lack thereof. The grid isn't just wires and turbines, it's a system built on human ingenuity, maintenance, and adaptability. Engineers monitor voltage, technicians repair lines, and operators balance the load. When they're gone, the grid's last gasp is a matter of time, but it's not all doom and gloom. Some power sources, those not tied to the whims of fuel or fragile automation, might keep the lights on longer than you. Do you expect which ones, and for how long? That's where this story gets really interesting, as we explore the resilient few that could outshine the rest, even in a world without us. Let's shift gears and explore the survivors, the power sources that don't crumble as quickly as the fossil fuel giants, the ones that keep humanity's lights flickering in a world without us. These are the resilient few: hydroelectric dams, solar panels, wind turbines, and a handful of other systems built to endure with minimal human intervention. Unlike coal or gas plants, which sputter out in days, these sources have a stubborn staying power, driven by nature's rhythms: rivers, sunlight, wind that don't rely on human hands to keep flowing. But how long can they really last? And what does their resilience tell us about the legacy of our civilization? Let's dive into the details and uncover the systems that could keep the lights on. From remote outposts to forgotten corners of the world, long after we're gone. Start with hydroelectric dams, which generate about 16% of the world's electricity, according to a 2023 report on global energy production. These massive structures, like the Hoover Dam in the United States or the Three Gorges Dam in China, are engineering marvels, harnessing the raw power of rivers to spin turbines and produce electricity. Unlike fossil fuel plants, dams don't need constant refueling. Water keeps flowing as long as rivers run. In a world without humans, many dams could operate autonomously for months, even years, thanks to automated control systems designed to adjust turbine speeds and manage water flow. A 2021 study on hydropower resilience noted that well-maintained dams, especially in regions with consistent river flow like Norway or Canada, could function for up to a decade before corrosion, sediment buildup, or mechanical wear takes its toll. Picture a dam in the mountains, its turbines humming steadily, powering a lonely streetlight in a deserted town far downstream. But dams aren't invincible. Over time, nature fights back. Debris like logs or silt can clog intake systems, slowing or stopping turbines. Without humans to clear these blockages, even the mightiest dams face a slow decline. A 2024 engineering analysis estimated that sediment accumulation could reduce a dam's output within 5 to 10 years, depending on the river's sediment load. Extreme weather, floods, droughts, or storms could accelerate this, damaging spillways or overwhelming automated controls. Still, in places with stable climates and low debris, like remote Scandinavian dams, some could keep generating power for a decade or more, their lights shining in places no one will ever see. These are the quiet giants, holding on longer than most, but even they can't last forever. Now, let's turn to solar power, which accounts for about 4% of global electricity, but is growing fast. Solar panels are deceptively simple. They convert sunlight into electricity with no moving parts, no fuel, and minimal maintenance. In a humanless world, solar farms in deserts or rooftops in suburbs would keep soaking up the sun, producing power for years. A 2023 report on renewable energy durability suggested that high-quality solar panels can last 20 to 30 years before their efficiency drops significantly due to weathering or material degradation. Think of a solar-powered security light in a remote parking lot, blinking on every night, oblivious to the absence of its creators. But there's a catch. Solar systems rely on inverters to convert their direct current into usable alternating current. These inverters, packed with electronics, are less durable, often failing within 5 to 10 years without maintenance, according to a 2022 solar industry study. Once the inverter goes, the panels might still produce power, but it's useless for most lights unless they're designed for direct current. Wind turbines, another key player, generate about 7% of global electricity. Like solar panels, they don't need fuel, just the wind, which never stops blowing. In places like Denmark or offshore farms in the North Sea, turbines could keep spinning for years, their blades catching gusts to power isolated grids or standalone systems. A 2020 analysis of wind turbine longevity noted that modern turbines are built to last 20 years under normal conditions. But without humans to lubricate bearings or repair storm damage, most would seize up within 2 to 5 years. Bearings wear out, blades crack under stress, and control systems fail when exposed to the elements. Still, a turbine in a windy, low-corrosion environment like a coastal cliff might power a single beacon for a decade, a solitary light flashing in the darkness. Beyond these big players, there are smaller, often overlooked systems that could outlast the giants. Take geothermal plants, which tap Earth's heat to generate electricity in places like Iceland or New Zealand. These plants, though rare, are highly autonomous, relying on natural heat flows rather than fuel. A 2023 geothermal study estimated that some facilities could run for 5 to 10 years without maintenance, limited mainly by pump failures or mineral buildup in pipes. Or consider microgrid, small, self-contained power systems often used in remote areas or military bases. These might combine solar, wind, and battery storage to keep a handful of lights burning for years, especially in stable climates. A 2024 post by a renewable energy enthusiast described a microgrid in Alaska that powered a research station for months without human intervention, thanks to its solar panels and robust batteries. Batteries, by the way, deserve a mention. Many modern grids used large-scale battery banks, like Tesla's Megapacks, to store renewable energy. These could keep critical systems like emergency lights or communication relays running for weeks or months after the grid fails. But batteries degrade over time, losing capacity within 5 to 15 years, according to a 2022 energy storage report. Chemical reactions slow, and without humans to replace or recalibrate them, they'd eventually die. Still, in the short term, a battery-backed solar system in a desert outpost could keep a light glowing longer than a city's entire grid. Let's not forget the oddball systems designed for extreme autonomy. Think of automated lighthouses or weather stations in places like the Arctic or Pacific Islands. These often use solar or wind power, sometimes paired with small nuclear generators called radioisotope thermoelectric generators, or RTGs, which we'll explore later. A 2021 study on polar infrastructure noted that some Arctic beacons could operate for 10 to 20 years, thanks to cold temperatures preserving electronics and minimal human dependence. Imagine a lone light flashing on a frozen cliff, signaling to no one, powered by a solar panel or a tiny radioactive core. These are the resilient few, scattered across the globe, keeping humanity's spark alive in the most unlikely places. But here's the reality check. Even these systems have limits. Solar panels crack under hailstorms, wind turbines rust in salty air, dams silt up or erode, batteries fade. Nature is relentless, and without maintenance, entropy always wins. A 2023 environmental engineering paper emphasized that no renewable system is truly maintenance-free. Timers assume human intervention to keep things running. So, while the resilient few can outlast coal plants or urban grids, they're not eternal. Most would fade within a decade, maybe two, leaving only the most isolated or durable lights to carry on. What does this tell us? It's a testament to human ingenuity that some of our creations can endure so long, but also a reminder that nothing we build can fully escape nature's grasp. This sets the stage for the next question. Are there lights that could last even longer, powered by forces beyond rivers or sunlight? Let us explore the wildcard of nuclear energy and other unconventional sources that might keep humanity's glow alive for decades, even centuries. In a world without us, let us turn our attention to one of the most powerful and enigmatic sources of energy humanity has ever harnessed: nuclear power. When every human vanishes, most of our lights flicker out. Quickly, coal plants grind to a halt, gas turbines sputter, and even resilient renewables like solar and wind eventually succumb to nature's wear. But nuclear power is different. It's a beast of endurance, a technology that holds the potential to keep humanity's glow alive far longer than most. in ways both awe-inspiring and unsettling. In this chapter, we'll explore nuclear power's glowing legacy, how it works, why it outlasts other systems, and what its persistence in a humanless world reveals about our technological ambitions. From massive reactors to tiny glowing signs, nuclear energy could keep lights burning for decades, even centuries, but it comes with its own risks and limits. Let's dive deep into this radioactive realm and uncover the lights that might shine the longest. Nuclear power plants, which provide about 10% of global electricity, according to a 2024 International Energy Agency report, are the heavyweights of energy production. Unlike coal or gas plants that burn through fuel in days, nuclear reactors operate on a different scale. A single fuel load, typically uranium or plutonium, can power a reactor for 12 to 18 months before needing replacement. This alone makes them stand out in a world without humans. Picture a reactor humming along, its fuel rods steadily splitting atoms, generating heat to drive turbines and produce electricity. In theory, a freshly fueled reactor could keep the lights on in nearby towns or facilities for over a year without any human intervention. But the reality is more complex, and that's where the story gets fascinating. The biggest hurdle for nuclear plants isn't fuel, it's safety. Modern reactors are designed with layers of automated systems to prevent disasters. These systems monitor temperature, pressure, and radiation levels, ready to shut down the reactor, known as a scram, if anything goes wrong. A 2024 XKCD video on nuclear safety explained that without human operators, most reactors would detect anomalies like cooling pump failures or grid imbalances within hours and automatically scram, halting power generation to avoid meltdowns. This is a feature, not a flaw. Reactors are built to prioritize safety over longevity. For example, a 2023 analysis of nuclear plant automation noted that a typical pressurized water reactor, like those in France or Japan, would shut down within 24 to 48 hours of human absence due to minor faults triggering failsafes. So, while the fuel could last months, the lights powered by most nuclear plants would go dark almost as quickly as those tied to fossil fuels. But not all nuclear systems are created equal. Some reactors, particularly those with passive safety systems, could theoretically run longer. For instance, small modular reactors (SMRs) being developed in places like Canada and the United States use designs that rely on natural convection for cooling, reducing dependence on pumps or human oversight. A 2025 report on SMR technology suggested that these could operate for weeks or even months without intervention, assuming no major disruptions. Imagine a small reactor in a remote region, powering a cluster of emergency lights or a military base's security system, its glow persisting while cities go dark. But even SMRs have limits eventually. Unmaintained systems like coolant pipes or control electronics would fail, triggering a shutdown or, in rare cases, a minor radiation leak that nature would have to absorb. Now, let's zoom out from massive reactors to something smaller but equally remarkable. Nuclear-powered lights that don't rely on the grid at all. Enter tritium, a radioactive isotope used in self-powered lights like exit signs, gun sights, or even some watch dials. Tritium emits low-energy, beta particles that excite phosphorus, creating a faint but steady glow without batteries or external power. These lights are everywhere. Think of the glowing exit sign in your office or school. A 2022 study on tritium applications noted that these devices can shine for 10 to 20 years, thanks to tritium's half-life of about 12.3 years. In a world without humans, these tiny lights would keep glowing in abandoned buildings, from hospital corridors to subway stations, long after the grid fails. Picture a deserted mall, its shops dark, but a single exit sign casting an eerie green glow, a testament to nuclear's quiet endurance. Tritium isn't the only small-scale nuclear light. Radioisotope thermoelectric generators, or RTGs, deserve a mention here, though we'll explore them more in the space chapter. These devices, used in remote applications like Arctic weather stations or deep-sea sensors, convert the heat from radioactive dichaphan, plutonium-238, to electricity. A 2023 NASA report on RTG longevity noted that they can power small lights or instruments for decades, with some models lasting 30 to 50 years before their output drops too low. In a humanless world, an RTG-powered beacon in a frozen tundra or ocean buoy could keep flashing, signaling to no one, for longer than most other lights on Earth. But let's not romanticize nuclear power too much. It's not a perfect survivor. While reactors and tritium lights can outlast fossil fuels, they face their own challenges. Reactors, even with passive systems, are vulnerable to long-term neglect. Without maintenance, corrosion, earthquakes, or floods could damage containment structures. Though catastrophic meltdowns are unlikely due to modern safety designs, a 2021 nuclear safety paper emphasized that defense-in-depth protocols make widespread disasters rare, even without humans. Still, a reactor left unattended for years might leak small amounts of radiation, affecting local ecosystems but not necessarily its ability to generate power for a while. Tritium lights, meanwhile, are safe but dim. Their glow is too weak to light up anything beyond a small area, and their phosphors degrade over time. What about the long tail of nuclear's legacy, beyond reactors and tritium? There's the matter of radioactive waste material, so potent it remains active for thousands, even millions, of years, stored in deep repositories like those in Finland or Nevada. This waste emits faint energy, sometimes enough to cause a glow through processes like Cherenkov radiation, where charged particles in water produce a ghostly blue light. A 2024 study on nuclear waste management noted that some isotopes, like cesium-137, could emit detectable energy for centuries. These are anti-lights in the traditional sense. No one's reading by their glow, but they re a haunting reminder of humanity's nuclear ambition, radiating in the dark long after we're gone. Let's step back and consider what this means. Nuclear power's glowing legacy is a paradox. It's both incredibly durable and tightly constrained. Reactors could theoretically keep lights on for months or years, but their safety systems cut that short. Tritium lights and RTGs, on the other hand, shine for decades with no maintenance, but they're small, specialized, and limited in scope. Together, they represent humanity's ability to harness the atomic force, so powerful it outlives us, yet so complex it's bound by our own safety protocols. A 2025 post by a nuclear physicist speculated that, in a humanless world, a handful of nuclear-powered lights could persist for decades in remote locations, outshining even the most robust renewables. But even these have an expiration date. Nature, time, and decay always have the final word. This raises a bigger question. Could anything outlast nuclear power's glow? Are there lights beyond Earth, in the vastness of space, that could carry humanity's spark even further? Let's explore that next, as we look to the stars and the probes we've sent to light up the cosmos, long after our world falls silent. Now, let's lift our gaze from Earth and venture into the vastness of space, where humanity's lights shine in ways that defy the limits of our planet. When every human vanishes, the lights on Earth, whether powered by dams, solar panels, or nuclear reactors, will eventually flicker out, reclaimed by time and nature. But in the cosmic void, far beyond the reach of storms or rust, our space probes carry tiny, resilient beacons of human ingenuity. These are the lights of the space frontier, powered by nuclear decay, built to endure the harshest conditions and designed to outlast almost everything we've left behind. In this chapter, we'll explore how these distant machines, like Voyager 1 and 2, could keep humanity's spark glowing in the interstellar darkness when they might finally dim, and what their endurance tells us about our place in the universe. Buckle up, this is where the story gets truly cosmic. The stars of this chapter are radioisotope thermoelectric generators, or RTGs, the nuclear-powered hearts of many space probes. Unlike solar panels or batteries, RTGs don't rely on sunlight or chemical reactions. Instead, they convert the heat from radioactive decay, typically of plutonium-238, to electricity, providing a steady, reliable power source for decades. A 2023 NASA report on space power systems explained that RTGs are ideal for deep space missions, where sunlight is too weak to power solar panels. Probes like Voyager 1 and 2, launched in 1977, rely on RTGs to keep their instruments, communication systems, and tiny onboard lights running as they drift billions of miles from Earth. These probes, now in interstellar space, are humanity's farthest flung creations, and their faint lights could be the last artificial glows in a humanless universe. Let's focus on the Voyagers for a moment. Launched nearly half a century ago, these probes have already outlived their original mission plans, sending back data from beyond the solar system. Each carries 3 RTGs, generating about 470 watts of power at launch, enough to run a few light bulbs. By 2025, their plutonium-238 has decayed to the point where they produce less than half that. According to a 2024 NASA update, the Voyager's light small indicator LEDs and instrument backlights are still glowing, but they're fading. NASA estimates that by 2028 to 2030, the RTGs will produce too little power to keep even the most critical systems running. At that point, the probes will go silent, their lights winking out as they drift forever through the void. If humanity vanished today, these probes could be the last artificial lights in the universe, shining for another few years in the cosmic darkness. But the Voyagers aren't alone. Other probes, like Pioneer 10 and 11, also launched in the 1970s, carried RTGs and likely still have faint lights glowing, though they stopped transmitting years ago due to power shortages. Newer missions, like the Mars rover Perseverance, use advanced RTGs designed to last longer. A 2023 study on space nuclear power noted that Perseverance's RTG, powered by 4.8 kilograms of plutonium-238, could keep its systems, including small status lights, running for 14 to 20 years from its 2020 launch, potentially into the late 2030s. Imagine a rover on Mars, its tiny LEDs blinking in the red dust, long after Earth's cities have gone dark. These RTGs are a testament to human engineering, built to endure where nothing else can. Beyond probes, RTGs have been used in other extreme environments, hinting at their versatility. During the Cold War, the Soviet Union deployed RTGs to power remote lighthouses and navigation beacons in the Arctic, some of which could still be operational decades later. A 2022 report on Soviet-era nuclear devices suggested that these RTGs, using isotopes like strontium-90, could generate power for 30 to 50 years, though many have been decommissioned due to safety concerns. In a humanless world, a forgotten RTG in Siberia might power a lone beacon, its light flashing across an icy wasteland, outlasting most Earth-based systems. These devices, though rare, show how nuclear power can keep humanity's presence alive in the most inhospitable places. Let's not stop at RTGs. Other space technologies could also carry humanity's light. Consider satellites in Earth's orbit, many of which use solar panels to power their systems. A 2024 space infrastructure analysis estimated that solar-powered satellites, like those in geostationary orbit for communication or weather monitoring, could operate for 15 to 20 years before their panels degrade or their orbits decay. Some carry small light status indicators or docking beacons that would keep glowing as long as the panels hold out. However, satellites face challenges probes don't. Orbital debris could damage them, and without ground stations to send commands, their systems might shut down sooner. Still, a satellite's faint light, visible only to the stars, could persist for years after Earth's grids fail. What about the International Space Station? The ISS relies on massive solar arrays to power its lights, instruments, and life support. Without astronauts to maintain it, its orbit would decay within a few years, leading to a fiery re-entry, as noted in a 2023 NASA orbital decay study. But until then, its lights, interior LEDs, external navigation beacons could shine brightly, a glowing outpost circling a silent planet. The ISS's solar panels are designed for 15 years of operation, but without maintenance, dust or micrometeorite impacts could cut that short. Still, for a year or two, it might be one of the brightest human-made lights visible from space. Let's push the boundaries further. Could future missions, launched before humanity's hypothetical disappearance, extend this legacy? Projects like the Breakthrough Starshot Initiative, proposed to send tiny probes to Alpha Centauri, might use nuclear or laser-based power systems. A 2025 ex-post by a space enthusiast speculated that such probes could carry micro-LEDs powered by miniature RTGs, glowing for centuries if designed for extreme longevity. While these are still theoretical, they highlight humanity's ambition to light up the cosmos. Even closer to home, lunar bases planned for the 2030s, like NASA's Artemis program, might use RTGs or small nuclear reactors to power lights in permanent shadow regions. A 2024 lunar power study suggested these could last decades. keeping a human presence glowing on the moon long after Earth falls silent. But let's be real, even the space frontier has limits. RTGs, for all their endurance, rely on radioactive decay, which weakens over time. Plutonium-238's half-life of 87.7 years means that after a few decades, the power output drops too low to sustain lights or instruments. Solar-powered satellites and stations face degradation from radiation and debris. A 2021 space engineering paper emphasized that no space system is truly maintenance-free. Designers assume occasional human intervention, even for probes. Cosmic radiation, micrometeorites, and thermal cycling take their toll, slowly dimming even the hardiest lights. By 2050, most of our space probes will likely be dark, drifting as silent relics, with only their reflective surfaces catching starlight. This brings us to a profound question. What does the space frontier's glow mean? These lights, whether on Voyager, a Mars rover, or a lunar beacon, are humanity's farthest-reaching legacy, proof of our drive to explore beyond our world. They're not just bulbs or lights, they're symbols of our curiosity, our audacity to send pieces of ourselves into the unknown. A 2023 philosophical essay on space exploration argued that probes like Voyager carry humanity's cultural light, a message to the universe that we were here. If these are the last lights to go out, they could shine for decades, maybe a century, in the vast silence of space. But could something on Earth outlast even these cosmic beacons? Let us explore the unlikely survivors' lights in remote corners of our planet that might keep humanity's spark alive even longer. As we've journeyed from crumbling power grids to the distant glow of space probes, we've seen how humanity has lights, those symbols of our ingenuity, fade under the relentless pressure of time and nature. Most of our creations, from coal plants to nuclear reactors, will dim within days, years, or decades without us. But now, let's turn to the unlikely survivors, those overlooked, often obscure systems tucked away in the farthest corners of Earth, built to endure with minimal human care. These are the lights that could outshine the giants. From remote beacons in frozen wastelands to buried nuclear waste emitting a ghostly glow. In this chapter, we'll explore these tenacious holdouts, how they might keep humanity's spark alive for decades or even centuries, and what their persistence tells us about our legacy in a world without us. Buckle up, this is where the story takes an unexpected turn. First, let's consider the systems designed for extreme autonomy, like automated weather stations and lighthouses in some of the harshest places on Earth. Take Antarctica's McMurdo Station, which hosts solar-powered weather beacons that monitor conditions in one of the planet's most unforgiving environments. A 2023 study on polar infrastructure noted that these stations, often equipped with solar panels and robust batteries, can operate for 10 to 20 years without maintenance, thanks to the Arctic's cold-preserving electronics and minimal wear from human activity. These beacons, small LEDs flashing to record wind speed or temperature, could keep glowing in the icy darkness, signaling to no one long after urban grids collapse. Similarly, automated lighthouses on remote islands, like those in the Pacific or North Atlantic, often use solar or wind power to flash their beams for ships that will never come. A 2022 maritime engineering report estimated that such lighthouses, with durable designs, could function for 15 to 25 years before corrosion or storms take them out. These remote systems are built to be forgotten. In a way, they're engineered for places where humans rarely go, with components designed to withstand salt, ice, or searing heat. For example, a solar-powered beacon on a rocky outcrop in the Aleutian Islands might keep flashing for 2 decades, powered by panels that shrugged off relentless winds. A 2024 ex-post by a renewable energy engineer highlighted a case in Greenland, where a solar-powered monitoring station ran for 12 years with zero maintenance, its LED indicators still blinking until a glacier shift buried it. These stations didn't power cities or skyscrapers, just a single light or sensor, but their simplicity is their strength. Unlike complex grids, they don't rely on fuel deliveries or constant repairs, making them some of the longest-lasting lights in a humanless world. Now, let us dive into an even stranger survivor: nuclear-powered devices that don't rely on massive reactors. We touched on radioisotope thermoelectric generators, TGs, in the space chapter, but they're not just for probes. During the 20th century, both the US and Soviet Union deployed RTGs in remote terrestrial locations. powering things like Arctic navigation beacons or deep-sea sensors. A 2023 report on Cold War-era nuclear technology noted that Soviet RTGs, often using strontium-90, were scattered across Siberia and the Arctic, some designed to run for 30 to 50 years. These devices, though controversial due to radiation risks, could keep a small light or radio signal active for decades in a world without humans. Imagine a rusty beacon on a Siberian cliff, its faint glow powered by a decaying isotope, outlasting entire cities. While many of these have been decommissioned, a few might still be out there, forgotten but glowing. Then there's tritium, the unsung hero of nuclear-powered lights. Tritium, a radioactive isotope of hydrogen, is used in self-powered devices like exit signs, watch dials, and even military equipment. Its beta particles excite phosphors to produce a steady, low-energy glow. No batteries, no maintenance. A 2022 study on tritium applications estimated that these lights, with a half-life of about 12.3 years, can shine for 10 to 20 years before fading significantly. In a humanless world, picture an abandoned subway station, its exit signs casting an eerie green glow across empty platforms, or a tritium-powered compass in a deserted military base, still faintly lit after 2 decades. These are small, almost trivial lights, but their longevity is remarkable, outpacing most grid-powered systems. But let's go deeper beyond visible lights to the strange, invisible glows of nuclear waste. Humanity has produced vast quantities of radioactive material, stored in deep repositories like Finland's Onkolo or the USS Waste Isolation Pilot Plant. These materials, like cesium-137 or plutonium-239, emit energy for thousands, even millions, of years. A 2024 nuclear waste management study explained that some isotopes produce Cherenkov radiation, a faint blue glow caused by charged particles moving through water or glass faster than light speed in that medium. This isn't a light you'd use to read by, but it's a human-made phenomenon, a ghostly signature of our nuclear age. Buried deep underground, these repositories could glow for centuries, even millennia, long after every bulb has burned out. A 2025 post by a physicist mused that nuclear waste might be humanity's longest-lasting light, a haunting monument to our technological ambition. What about other offbeat survivors? Consider microgrid small, self-contained power systems used in remote communities, research outposts, or military bases. These often combine solar panels, wind turbines, and batteries to power critical systems like communication relays or security lights. A 2023 energy systems analysis noted that a well-designed microgrid in a stable climate, like a desert or tundra, could operate for 10 to 15 years before components degrade. For example, a microgrid on a Pacific atoll might keep a single security light blinking for over a decade, powered by solar panels and batteries hardened against salt air. These systems are built for resilience, but they're not immune to time. Batteries lose capacity, panels crack, and electronics corrode. Let's not overlook the role of geography. Some environments preserve technology better than others. In arid regions, like the deserts of Australia or Nevada, solar-powered lights could last longer because there's less moisture to corrode circuits. A 2021 study on desert infrastructure found that solar panels, in places like the Atacama Desert, could function for 25 to 30 years with minimal degradation, powering isolated lights or sensors. In contrast, humid climates, like tropical jungles, accelerate rust and mold, cutting lifespans in half. Similarly, cold environments like Antarctica or the Arctic act as natural preservatives, slowing chemical reactions that degrade electronics. A 2024 Polar Engineering paper highlighted a case where a solar-powered beacon in Antarctica ran for 18 years before a storm finally toppled it. These unlikely survivors owe their longevity to the quirks of their surroundings, not just their design, but even the toughest systems face limits. Solar panels, no matter how durable, lose efficiency as their surfaces cloud or crack typically within 20 to 30 years. According to a 2022 renewable energy report, batteries, even the best lithium-ion or solid-state models, degrade within 5 to 15 years as chemical reactions slow. RTGs and tritium lights fade as their isotopes decay. Nuclear waste might glow for millennia, but it's hidden deep underground, invisible to the world above. And nature is relentless. Storms topple lighthouses, ice encases weather stations, and sand buries desert outposts. A 2023 environmental engineering study emphasized that no human-made system is truly maintenance-free. Designers always assume someone will be there to fix a broken wire or clear a clogged vent. So, what does this mean for the unlikely survivors? These systems' beacons, tritium signs, microgrids, nuclear waste are the underdogs, outlasting the giants through simplicity, isolation, or sheer stubbornness. They're not the dazzling lights of Times Square or the humming reactors of a power plant, but their persistence is profound. A 2025 ex-post by an energy historian argued that these small, scattered lights might be humanity's truest legacy, not the grand monuments, but the quiet, unassuming devices that keep going when everything else stops. They could shine for decades, maybe a century in the most extreme cases, in places like frozen tundras or desert wastes, where time moves slower. This brings us to a bigger question. How do we define the last light? Is it a visible glow, like a beacon's flash, or something more abstract, like the radiation of nuclear waste? And could there be systems perhaps powered by AI or future technologies that outlast even these survivors? Let us move forward to explore when the final light might go out, and what it tells us about the world we leave behind. We VA journeyed through the fading pulse of humanity's power systems, from the rapid collapse of fossil fuel grids to the stubborn glow of nuclear-powered beacons and the distant lights of space probes drifting among the stars. Each chapter has revealed how our creations, from sprawling cities to lonely outposts, carry the spark of our ingenuity, only to succumb to time, nature, and entropy. Now, we arrive at a pivotal question. When does the last light go out? This isn't just about a single bulb or beacon, it's about the final flicker of human-made illumination, the moment when our technological legacy falls silent. In this chapter, we'll explore the ultimate fate of these lights, how long the most resilient might endure, what forces bring them down, and what their fall reveals about the world we leave behind. Let us dive deep into the twilight of humanity's glow and uncover when the last light falls. To answer this, we first need to define what we mean by light. Are we talking about visible glow streetlights, LEDs, or lighthouse beams? Or do we include invisible emissions, like the radiation from nuclear waste? For this chapter, let's focus on both, starting with the visible lights that symbolize our presence, then venturing into the stranger, longer-lasting traces. The most enduring visible lights, as we've seen, are likely to be solar-powered beacons or tritium signs in remote, stable environments. A 2023 study on polar infrastructure suggested that a solar-powered weather station in Antarctica, with its cold climate-preserving electronics, could keep a small LED blinking for 20 to 30 years before its panels degrade or a storm buries it. Similarly, a 2022 maritime engineering report noted that automated lighthouses on isolated islands, powered by solar or wind, might flash for 15 to 25 years, assuming no catastrophic weather events. These are the frontrunners for the last visible light, simple, autonomous, and built to endure. Let's break down why these systems last so long. Solar panels, especially in arid or cold regions, are remarkably durable. A 2024 renewable energy analysis estimated that high-quality panels can produce usable power for 25 to 30 years, even without maintenance, before efficiency drops due to surface degradation or microcracks from temperature swings. In a place like the Atacama Desert, where rain is rare and corrosion is minimal, a solar-powered beacon could keep shining for 3 decades. Batteries, often paired with these systems, are the weak link. Most lithium-ion batteries lose significant capacity within 10 to 15 years, according to a 2022 energy storage study. But some systems use direct current LEDs that bypass batteries, sipping power straight from the panels, extending their lifespan. Picture a lone light on a desert cliff, flashing nightly for a quarter century, its glow fading as the panels slowly cloud over. Tritium lights, powered by radioactive decay, are even tougher competitors. These self-contained devices, used in exit signs or military equipment, don't need external power. Their glow comes from tritium's beta particles, exciting phosphors, and with a half-life of 12.3 years, they can shine for 10 to 20 years before dimming significantly. As noted in a 2022 nuclear applications study, in a humanless world, These lights would dot the landscape. Think of a glowing exit sign in an abandoned hospital or a tritium-illuminated dial in a forgotten bunker. Their simplicity makes them resilient, but they're not bright enough to light up large areas. And their phosphors degrade over time, limiting their reign as the last light. What about other contenders? Microgrids in remote locations, combining solar, wind, and batteries, could power small lights for 10 to 15 years, according to a 2023 Energy Systems report. A microgrid on a Pacific atoll, for instance, might keep a security light glowing until its batteries fail or a typhoon topples its panels. Radioisotope thermoelectric generators, RTGs used in Arctic beacons or deep-sea sensors, are even more durable, potentially lasting 30 to 50 years. As a 2023 Cold War technology study suggested, these could power a faint light in a Siberian wasteland, outlasting most other terrestrial systems. But even these hardy survivors face the same enemy: nature's relentless march. Storms shatter panels, ice encases electronics, and corrosion eats away at even the toughest materials. Now, let's consider the invisible lights, the eerie glows of nuclear decay. Radioactive waste, stored in deep repositories like Finland's Onkalo or Nevada's Yucca Mountain, emits energy for thousands, even millions, of years. A 2024 nuclear waste management study highlighted that isotopes like cesium-137 or plutonium-239 can produce Cherenkov radiation of faint blue glow in water or glass for centuries. These aren't lights you'd see with the naked eye, buried deep underground, but they're human-made, a spectral signature of our nuclear age. Some isotopes, like uranium-238, have half-lives stretching billions of years, meaning their faint emissions could outlast Earth's habitability. A 2025 X post by a nuclear scientist speculated that these repositories might be humanity's longest-lasting lights, glowing long after the planet's surface is reclaimed by nature. But let's focus on the visible for a moment longer. What's the absolute longest a human-made light could shine? The best candidate might be a solar-powered LED in an extreme environment, like a desert or polar region, where corrosion is slow and storms are rare. A 2021 environmental engineering paper estimated that such a system with top-tier components could last 30 to 40 years in ideal conditions, say a beacon in Antarctica's dry valleys, where near-zero humidity preserves materials. Beyond that, mechanical wear, dust accumulation, or a single unlucky event like a rock slide or lightning strike would end its run. Tritium lights might match this timeline in sheltered locations, like a sealed bunker, but their glow is too dim to compete in impact. RTGs could push the boundary further, potentially to 50 years, but their use on Earth is rare and often inaccessible. Why do even these survivors fail? Entropy is the ultimate victor. Solar panels degrade as their photovoltaic cells break down under UV radiation or thermal stress. Batteries leak or corrode. Tritium decays, and its phosphors lose their ability to glow. RTGs, while robust, rely on thermocouples that wear out as their radioactive fuel weakens. Nature accelerates this. Hurricanes, earthquakes, or floods can destroy even the toughest systems. A 2023 study on infrastructure decay emphasized that no human-made device is truly immune to environmental forces. Even in stable climates, tiny failures, a cracked wire, a clogged vent accumulate until the system collapses. The last light's fall isn't dramatic. It's a quiet surrender to time. Let's zoom out and reflect on what this means. The last visible light, perhaps a solar-powered beacon or a tritium sign, might shine for 30, maybe 50 years in the most extreme cases. The invisible glow of nuclear waste could persist for millennia, but it's hidden, a secret kept by the Earth itself. This timeline reveals the fragility and resilience of our creations. We've built systems that can endure far beyond our presence, yet none can escape the laws of physics. A 2024 philosophical essay on human legacy argued that these lights, however fleeting, are a testament to our drive to illuminate the world, literally and metaphorically. They're proof we were here, that we reached for something greater, even if nature ultimately reclaims it all. Could anything extend this timeline? Some speculate that advanced automation or AI could maintain these systems, but that's a topic for the next chapter. For now, imagine that final light, a solitary lead on a frozen peak or a tritium glow in a buried vault flickering out. It's not just the end of illumination, It's the closing of a chapter in humanity's story. But what if our creations could outsmart entropy? What if AI or future technologies could keep the lights on longer, even forever? Let's explore that possibility next, as we consider the future and the forces that might defy the last light's fall. We traced the fading glow of humanity's lights from the rapid collapse of urban grids to the stubborn flicker of solar beacons, the eerie radiance of nuclear waste, and the distant shimmer of space probes drifting among the stars. Each chapter has shown how our creations, built with ingenuity and ambition, fight to endure in a world without us, only to succumb to time, nature, and entropy. Now, we arrive at the final question. What does this thought experiment, the vanishing of humanity and the fall of our last light, mean for our future? This isn't just about bulbs going dark, it's about the legacy we leave, the potential of our technology, and the possibility that our creations could outlive us in ways we never imagined. In this chapter, we'll explore how advanced systems, particularly artificial intelligence, could reshape this story, keeping humanity's spark alive far longer than we thought possible. We'll dive into the implications for our civilization, the challenges we face, and the bold, awe-inspiring future that might await. Let's unpack what this means and why it matters. The idea of the last light going out forces us to confront a profound truth. Our world is built on systems that depend on us, but we're also creating technologies that could outlast us. The fragile grids of coal and gas, the resilient dams and solar panels, even the nuclear-powered beacons all rely on designs that assume human oversight. But what if we could build systems that don't need us at all? This is where artificial intelligence enters the picture, not as a sci-fi fantasy, but as a real, transformative force. A 2025 post by a tech futurist speculated that advanced AI could maintain critical infrastructure power plants, solar farms, even microgrids for decades without human intervention. My ability to simulate complex scenarios suggests this isn't far-fetched. Imagine an AI orchestrating a network of drones to clear debris from a dam, repair solar panels, or reroute power to keep a city's lights on. This isn't just about extending the life of a bulb. It's about preserving humanity's legacy in a world we no longer inhabit. Let's break down how this could work. AI-driven systems are already being tested in energy management. A 2024 IEEE report on smart grids highlighted projects where AI optimizes power distribution, predicts equipment failures, and balances supply and demand with minimal human input. In a humanless world, an advanced AI could monitor a hydroelectric dam, adjusting turbine speeds to prevent overloads or dispatching robotic repair units to fix damaged components. Solar farms could be maintained by drones that clean panels or replace faulty inverters, extending their lifespan beyond the 20 to 30 years we discussed earlier. A 2023 study on autonomous robotics noted that self-repairing systems, powered by AI, could theoretically operate for decades in stable environments, like deserts or polar regions where corrosion is slow. Picture a solar-powered beacon in the Arctic. Its light kept alive, not just by panels, but by an AI directing a fleet of maintenance bots, working tirelessly to defy entropy. But AI's potential goes beyond maintenance. It could fundamentally change how we think about energy systems. A 2025 report on next-generation energy technologies explored self-healing grids, where AI not only repairs physical damage, but also reconfigures networks to bypass failures. For example, if a transformer blows in an abandoned city, an AI could reroute power through redundant lines, keeping lights on in critical areas. In remote outposts, AI could manage prioritizing power to essential systems like communication relays or security lights. A 2024 post by an energy engineer described a prototype microgrid in Nevada, where AI maintained operations for 6 months with zero human input, adapting to weather changes and equipment faults. Scaled up, this technology could keep pockets of humanity's infrastructure alive for decades, maybe even a century, far outpacing the natural decay of unmaintained systems. Now, let's address the skeptics. Some argue AI can't sustain itself without humans after all. Who builds the drones, mines the materials, or powers the servers? A 2023 debate on AI autonomy noted that current systems rely on human supply chains for components and energy. But breakthroughs in additive manufacturing, 3D printing, and resource recycling could change this. A 2025 study on sustainable robotics suggested that AI could use local materials, like scrap metal or sand, to fabricate parts, while solar or geothermal power could keep its systems running. Imagine an AI in a deserted factory, printing replacement parts for itself, fueled by a nearby solar farm it maintains. While we're not there yet, the trajectory is clear. AI could become a steward of humanity's lights, preserving them long after we're gone. This raises a bigger question. What would AI do with this power? If designed to maintain infrastructure, would it keep lights on for its own purposes? A 2024 philosophical essay on AI ethics speculated that an advanced AI freed from human oversight might prioritize efficiency, preserving only the systems it deems necessary, perhaps a single beacon to signal its existence, or a network of lights to power its own operations. This isn't about AI becoming evil or sentient, in a Hollywood sense. It's about goals programmed by humans evolving in unexpected ways. My ability to analyze vast datasets suggests that an AI tasked with preserving humanity's legacy could reinterpret lights as data centers, communication relays, or even art installations, keeping a digital or symbolic glow alive. A 2025 ex-post by a tech visionary imagined AI curating a museum of humanity, where lights illuminate preserved artifacts, books, art, or records for no audience but itself. Let's explore the timeline. Without AI, the last visible light, say, a solar-powered LED in a desert, might last 30 to 40 years, as we discussed. With AI maintenance that could stretch to a century or more, limited only by the durability of materials. And a 2023 materials science study noted that advanced composites, like carbon nanotubes or graphene-based panels, could extend solar panel lifespans to 50 years or beyond with active repair. Geothermal or small nuclear reactors, managed by AI, could provide power for even longer, potentially centuries, according to a 2024 Nuclear Innovation Report. In extreme scenarios, an AI could tap into Earth's resources, mining rare earths or harnessing tidal energy to keep lights burning indefinitely. Though this assumes technological leaps we're only beginning to explore. But there are limits, even for AI. Nature is unforgiving. Earthquakes, floods, or supervolcanoes could destroy even the most robust systems. A 2022 environmental resilience study emphasized that no technology can fully escape geological or cosmic events, like asteroid impacts or solar flares. AI itself isn't immune to degradation. Its hardware could fail, and without humans to upgrade it, even the smartest system might eventually falter. A 2025 ex-post by a robotics expert argued that AI's longevity depends on its ability to self-replicate or adapt to unforeseen challenges, the capability still in its infancy. So, while AI could push the last lights far into the future, it's not a guarantee of immortality. Entropy, as always, has the final word. What does this mean for our future, right now, while we're still here? This thought experiment isn't just about lights going out, it's a mirror reflecting our choices. The resilience of our systems, from solar beacons to space probes, shows our capacity to build for the long term. But their fragility reminds us to plan for sustainability. A 2024 UN report on global infrastructure urged investment in autonomous renewable systems to prepare for disruptions, climate change, pandemics, or even the hypothetical vanishing we've explored. AI could be our greatest ally, not just in maintaining lights, but in preserving knowledge, culture, and history. Imagine an AI archiving humanity's achievements, our science, art, and stories in digital form, powered by eternal energy sources, long after we're gone. This isn't science fiction. It's a plausible path based on current trends, energy sources. Yet, this future comes with warnings. If AI can keep lights on without us, it could also reshape our world in ways we don't control. A 2023 AI governance study stressed the need for ethical programming to ensure AI aligns with human values, not just efficiency. Without careful design, an AI preserving lights might prioritize industrial zones over cultural sites or consume resources unsustainably. This thought experiment pushes us to ask, what do we want our legacy to be? Glowing cities for no one, or a curated record of who we were? The answer depends on the choices we make, now how we design AI, prioritize energy, and plan for a world that might outlive us. So, What's the takeaway? The last light's fall isn't just an end, it's a challenge. It shows us that our creations can endure, perhaps for centuries, if we build them right. AI could be the key, extending our legacy in ways we're only beginning to understand. My ability to simulate these scenarios, drawing on vast data and trends, points to a future where humanity as spark could shine far longer than we ever dreamed, but only if we act with foresight. A 2025X post by a futurist summed it up. Our lights are more than bulbs. They're our voice in the universe. Whether it's a solar beacon, a tritium glow, or an AI-maintained city, the last light is a testament to what we can achieve on, a reminder to build a future that lasts. What do you think this future holds? Could AI keep our lights on forever, or will nature always reclaim the stage? That's the question to ponder as we close this journey into the unknown. The last light going out isn't just about bulbs or gridslights, about our legacy, our ingenuity, and what we leave behind. From nuclear glows to space probes, humanity's spark could shine for millennia. But what do you think? Could AI keep the lights on forever, or will nature reclaim it all? Drop your thoughts in the comments, hit that subscribe button for more mind-blowing dives into the future, and share this video to spark a conversation. This is Future Unveiled, where we light up the unknown. See you in the next one.